Alright, object-oriented programming part 2, and I believe we're going over polymorphism in Rust. Using trait objects that allow for values of different types. Here we go. In chapter 8, we mentioned that one limitation of vectors is that they can store elements of only one type. We created a workaround in listing 8-10 where we defined a spreadsheet cell enum that had variants to hold integers, float, and text. This meant that we could store different types of data in each cell and still have a vector that represented a row of cells. This is a perfectly good solution when our interchangeable items are a fixed set of types that we know when our code is compiled. However, sometimes we want our library user to be able to extend the set of types that are valid in a particular situation. To show how we might achieve this, we'll create an example graphical user interface GUI tool that iterates through a list of items, calling a draw method on each one to draw it to screen. A common technique for GUI tools. We'll create a library crate called GUI that contains the structure of a GUI library. This crate might include some types for people to use, such as button or text field. In addition, GUI users will want to create their own types that can be drawn. For instance, one programmer might add an image and another might add a select box. Alright, so let's go back to here real quick. The overarching topic is polymorphism, which was defined in the last video, but just to summarize, it's the ability to have different objects satisfy a constraint within a function and be used the same way. So in terms of inheritance, that's typically parent class and child class. In the function, you can say that this needs something of type parent, but the child class satisfies it, and this can be used. And it's polymorphism because those are two separate objects. In Rust, we do it differently, and they're showing how in chapter 8, we actually had an example of us doing something similar. So yeah, in listing 8, we had an example where in the spreadsheet, we had an enum, right? And then we created 3 different variants, and one variant held integers, one held float, one held text. So those are 3 different things, these variants, they're each separate. But we were able to classify them as a enum of one type. And because of that, we were able to put those 3 different types into our, we were able to put that type with those 3 different variants into our vector. And this is similar to polymorphism. We have a vector that by definition can only have one type, but our type seemingly has 3 different variants and they hold different types within them. So it holds, and this is a completely good solution if you know all of the different types and items and stuff that you need at compile time. If you do not know them at compile time, then you can't possibly define enums to satisfy your requirements. So that brings us to this example that we're about to write, which seemingly is going to show us how to do something that's polymorphic at runtime via a GUI example, creating like a GUI library. We won't implement a fully fledged GUI library for this example, but we'll show how the pieces would fit together. At the time of writing the library, we can't know and define all the types other programmers might want to create, but we do know that GUI needs to keep track of many values of different types, and it needs to call a draw method on each of those different typed values. It doesn't need to know exactly what will happen when we call the draw method, just that the value will have that method available for us to call. I see. So here, going back to what I was stating up here and how we need to, this example is about creating something that's polymorphic at runtime. The situation is we're creating a GUI library, right? And in the GUI library, it is common for the different components in this library to have a method called draw. And what this does is it draws something to screen. So to make this polymorphic at runtime, take a step back. It draws something to screen. Now for a GUI library, I, as the writer of said library, can create XYZ fields, like say button or text field, which they mention up here. but somebody else might create an image or a select box. And we would want their image to be able to be drawn to screen and their select box to be able to draw on the screen. So this is not necessarily at runtime, because depending on how they implement it, it might not be at runtime, it might be at compile time, but this is the idea of just post something being created, adding something else that fits into this sort of box and can be used the same way as everything else. And more or less, these things will have to have draw on it, because we will expect them to have the value. We expect the value to have the method available to us. So image and select box will have to have draw on it. And then the GUI should be able to call draw on those newly created components, image and select box, and have them work as expected, or has the author of those things expected. To do this in a language with inheritance, we might define a class named component that has a method named draw on it. The other classes, such as button, image, select box, would inherit from component and thus inherit the draw method. They could each overwrite the draw method to define their custom behavior, but the framework could treat all of the types as if they were component instances and call draw on them. But because Rust doesn't have inheritance, we need another way to structure the GUI library to allow users to extend it with new types. Alright, so from here, everything but the last sentence, they're going over how a language that has inheritance would solve this problem. They could create a class called component, and that has a draw method on it, and then they can create their children, which can be button, image, and select box, and all of those would have a draw method on it. But let's say the function that's using them, that you pass it into, the only thing it will want is component. But because these button, image, and select box are children of component, they satisfy a component, and this can be used in the same way. And then the code that calls draw just expects all of them to have draw, because they will, because they're all children of component. And then each of the child classes can just override it themselves and do what they need to for their individual draw methods. So we need to try to replicate this type of functionality in Rust, and that's what we're about to do. And based on this topic right here, it looks like we're going to do that via traits. Defining a trait for common behavior. To implement the behavior we want GUI to have, we'll define a trait named draw that will have one method named draw. Then we can define a vector that takes a trait object. A trait object points to both an instance of a type implementing our specified trait, as well as a table used to look up trait methods on the type at runtime. We create a trait object by specifying some sort of pointer, such as a reference or a box mark pointer, then the dynamic keyword, and then specifying the relevant trait. We'll talk about the reason trait objects must use a pointer in Chapter 19 in the section Dynamically Sized Types and the Sized Trait. We can use trait objects in place of generic or concrete type. Wherever we use a trait object, Rust type system will ensure at compile time that any value used in that context will implement that trait's object's trait. Consequently, we don't need to know all of the possible types at compile time. I see. So this was a lot of words, and it was sort of kind of complicated to read, but what they're saying here is that we can define a trait and then use that trait as the requirement of, let's say, a function, right? We can say that the object must have this trait, or actually taking a step back, instead of doing like the trait bounds, we can seemingly say this function takes this trait, and then any object that satisfies that trait can go in there. So if I'm thinking about this correctly, we can define a trait. In this function signature, we can say that we need something of this trait, and then we can define objects, different objects that satisfy this trait, let's say button, select box. And now, because they satisfy this trait, we can use any of these objects in that function. That's what I'm getting from this. We've mentioned that in Rust, we refrain from calling structs and enums objects to distinguish them from other languages' objects. In a struct or enum, the data in the struct fields and the behavior in implementation blocks are separated, whereas in other languages, the data and behavior combined into one concept is often labeled as an object. However, trait objects are more like objects in other languages in the sense that they combine data and behavior. But trait objects differ from traditional objects in that we can't add data to a trait object. Trait objects aren't as generally useful as objects in other languages. Their specified purpose is to allow abstractions across common behavior. Alright, so seemingly what I described up here was a trait object in Rust. Listing 17-3 shows how to define a trait named draw with one method named draw. So let's read through this. Source libs, public trait draw, and then we define a method called draw. This syntax should look familiar from our discussion on how to define traits in chapter 10. Next comes new syntax. Listing 17-4 defines a struct named screen that holds a vector named components. This vector is often of type box dynamic draw, which is a struct object. It's a stand-in for any type inside a box that implements the draw trait. Okay. So we have public, we have struct, we have screen, public components, and we have a vector of, we have a smart pointer box to anything that implements the dynamic draw. Okay. From my understanding, this is seemingly a vector of anything that implements draw. So like I was saying earlier, if box and select, item, and image all implement the draw trait, then they can just be placed within this vector, seemingly. Let me read on a little bit more before I write this out. On the screen struct, we'll define a method named run that will call the draw method on each of its components, as shown in listing 17-5. So screen, implementation block, we have a public method called run, and is iterating over the components and calling draw on them. So yeah, that makes sense, because we need to be able to call draw on these things. So I think I am correct. This works differently from defining a struct that uses a generic type parameter with trait bounds. A generic type parameter can only be substituted with one concrete type at a time, whereas trait objects allow for multiple concrete types to fill in for the trait object at runtime. For example, we could have defined a screen struct using a generic type and a trait bounds in listing 17-6. Oh, okay, I think I understand this. Let's read through this first and I'll give my summary. So here we're writing the same thing, seemingly, with the generic type parameter, the trait bounds. We have public struct, we have screen. It takes a type T that implements draw and then has the components of that list. So here is the main difference, right? If you write it this way, then anything that implements draw can be passed in. However, T is constrained to only be that type. So if we passed in button, we couldn't pass in image because those are two different objects, and thus there are two different T's. That's not allowed. So what they're saying here, seemingly the main difference is between this implementation and the one above it, is that when we write it this way, we're not limited to only one struct that implements this trait. We can use multiple structs that implement this trait. Whereas here, we're only limited to the one. And that's generally how we use the trait bounds. We bind it to one like struct, and then we use that consistently. And I should have continued reading. I didn't finish it, but they have the implementation block, and the implementation block is more or less the same, with the statement of the generic T, which is isolated to only one struct. This restricts us to a screen instance that has a list of components, all of type button or all of type text field. If you only ever have homogeneous collections, using generics and trait bounds is preferable because the definition will be monomorphized at compile time to use the concrete type. On the other hand, with the method using trait objects, one screen instance can hold a vector that contains a box button as well as a box text field. Let's look at how this works, and then we'll talk about the runtime performance implications. Alright, so let me go write this real quick because I'm curious, just in case we use this again. This is from the last video. Don't need any of this. So this syntax is the same. Public trait draw. What is different is the screen. We have box and dynamic. And then I'm not exactly sure why they need box here. They're probably just going to explain it. But we noticed that when they described it earlier, or recently, they made sure that the button was in a box and that the text field is also in a box. So that seems mandatory. In terms of iterating over components, it's written this way. And let's move on to the next section. Implementing the trait. Now we'll add some types that implement the draw trait. We'll provide the button type. Again, actually implementing a GUI library is beyond the scope of this book, so the draw method won't have any useful implementation in its body. To imagine what the implementation might look like, a button struct might have the fields width, height, label as shown in listing 17-7. Alright, so to note, the idea or concept of building an entire GUI library is well beyond the scope of this book. We're just drawing out skeletons implementations to give an idea of what this would look like. And here we have the button, right? We have the width, height, and label, which the button needs to have its size and buttons have labels. That makes sense. And then button will implement draw for button, and then we will have the draw, which will be the draw for button, what is needed to draw to screen. So just, we're not going to be running anything, at least I don't think so, but I'm going to have it here anyway. The width, height, and label fields on button will differ from the fields on other components, such as a text field type, that might have those fields plus a placeholder field instead. Each of the types that we want to draw on the screen will implement the draw trait, but we'll use different code in the draw method to define how to draw that particular type, as button has here, without the actual GUI code, which is beyond the scope of this chapter. The button type, for instance, might have an additional implementation block containing methods related to what happens when a user clicks the button. These kinds of methods won't apply to types like text field. Alright, so here they're just going over like a way of creating the GUI application with the different components. And we already wrote out button, and button has width, height, and label, which makes sense for a button. For a different component, we may need other fields. For example, what do they call it? A placeholder field, right, for the actual text field. And now each of these components, button's going to have its own draw, which could button's going to have its own draw, which is going to dictate how it gets drawn to the screen. And the implementation block for a button may also include other methods. For example, what happens when the user clicks it, right? Because that makes sense, buttons get clicked. Text fields don't get clicked, so that's not going to be there. But a text field is going to have its own implementation of draw, and then that dictates how it gets drawn to the field. And then when we go to screen, since screen can have both button and text fields, during the run, it just calls the draw method on each of the components, which will individually look at the draw implementation and then do what it needs to do. If someone using our library decides to implement a select box struct that has width, height, and option fields, they implement the draw trait on the select box type as well, as shown in listing 17-8. Alright, so here, this is seemingly an example of an external user, somebody that's not the library author, trying to extend the package GUI, right? So what they do first is they import the trait draw, and then they create their struct select box, and then they implement draw for select box. And because select box is now has an implementation of draw for the trait draw, it should work as all the other components within the library work, and the screen can draw to screen in the run. Our library user can now write their main function to create a screen instance. To the screen instance, they can add a select box and a button by putting each in a box to become a trait object. They can then call the run method on the screen instance, which will call draw on each of the components. Listing 17-9 shows its implementation. I'm going to expand this. This code is definitely not being meant to run, so we can just look at it here. Scroll up. So here we have, again, this is the external user, somebody that's not the library author, or somebody using the package externally. They're importing it. So they import screen and button, and in their main function, they create a screen. They have the list of components that they're creating. Box new, they're using their implementation of select box, which they created in their package, which we saw earlier. It has their width, height, and their options. And then they're also adding something that was native to the library, the button component, right here, which we also defined earlier. And then they're calling run on it. And then run, as we know, is going to iterate over these components and then call their draw method so it can draw them to screen. When we wrote the library, we didn't know that someone might add the select box type, but our screen implementation was able to operate on the new type and draw it because select box implements the draw trait, which means it implements the draw method. This concept of only being concerned with the messages a value responds to rather than value's concrete type is similar to the concept of duck typing in dynamically typed languages. If it walks like a duck and quacks like a duck, then it must be a duck. In the implementation of run on screen in listing 17-5, run doesn't need to know what the concrete type of each component is. It doesn't check whether a component is an instance of a button or a select box. It just calls the draw method on the component by specifying box dyn draw as the type of values in the component's vector. We define screen to need values that we can call the draw method on. Alright, so here's just a basic summary of what we've just learned. And that is, so in the components, which I can just bring that up again. So this component's vector box dyn draw, where we have the trait object. Well, we define what the traits need, but the trait object would be the box and anything that implements draw. This vector takes different trait objects. We can pass in a button, we can pass in the select box, we can pass in image. It doesn't matter. As long as that that struct implements the draw trait, we're good. And that's all it cares about. The concept of this idea is very similar to duck typing, where if it looks like a duck and quacks like a duck, it must be a duck. And the reason they say that is because this type object, this trait object, only cares that draw is satisfied, which another way of saying that it only cares that the structs that are passed in have a draw method. And as long as they have a draw method, everything is good. We don't care about the concrete type at all. The advantage of using trait objects and Rust type system to write code similar to code using duck typing is that we never have to check whether a value implements a particular method at runtime or worry about getting errors if a value doesn't implement a method, but we called it anyway. Rust won't compile our code if the values don't implement the traits that the trait object needs. I see. Okay. So here they're stating the advantage of doing this in Rust opposed to doing it in a language that actually has duck typing. And the advantage is that even though Rust, in terms of trait objects, only cares that the underlying trait methods are satisfied, and thus any struct that's passed in, it checks to see whether it has those methods, right, for the trait. But that check is done at compile time, as in if you try to pass in a struct that doesn't implement that trait, then the code is not going to compile. So what this means is that we're never going to have a runtime error, or we never have the overhead of having this checked at runtime. Things like that are just completely disregarded, which can be an issue in other languages that actually implement duck typing. For example, in listing 17-10 shows what happens if we try to create a screen on a string as a component. I can just expand this. Use GUI stream. So here we import screen from the package that we created for GUI. And in the component section, we try to put in a string. And this string does not implement our draw trait. We haven't even imported draw. And then we try to run it. This will give us a compile time error. So we'll get this error because string doesn't implement the draw trait. And the error states the trait bound string and then draw is not satisfied. The trait GUI draw is not implemented for string. Note, required for the cast to the object type draw. So this is an example of how Rust is using its type system to check at compile time whether or not this dynamic-like aspect of the language is satisfied. This error lets us know that either we're passing something to screen we didn't mean to pass and we should pass a different type, or we should implement draw on string so that screen is able to call draw on it. And yeah, that's basically what it's telling us here in this error. Trait objects perform dynamic dispatch. Recall in the performance of code using generic section on chapter 10, our discussion on the monomorphization process performed by the compiler when we use trait bounds on generics. The compiler generics non-generic implementation of functions and methods for each concrete type that we use in place of a generic type parameter. The code that results from monomorphization is doing static dispatch, which is when the compiler knows what method you're calling at compile time. This is opposed to dynamic dispatch, which is when the compiler can't tell at compile time which method you're calling. In dynamic dispatch cases, the compiler emits code that at runtime will figure out which method to call. When we use trait objects, Rust must use dynamic dispatch. The compiler doesn't know all of the types that might be used with the code that is using trait objects. So it doesn't know which method implemented on which type to call. Instead, at runtime, Rust uses the pointers inside the trait object to know which method to call. There is a runtime cost when this lookup happens that doesn't occur with static dispatch. Dynamic dispatch also prevents the compiler from choosing to inline a method's code, which in turn prevents some optimizations. However, we did get extra flexibility in the code that we wrote in listing 17-5, and we were able to support in listing 17-9. So it's a trade-off to consider. All right, here, so in the first paragraph, they're going over static dispatch and dynamic dispatch. Static dispatch is something they already informed us of in chapter 10. And they did it when they were telling us about generics and the type parameter. Now, if you recall, what the type parameter allows us to do is that we can write code that says for a generic T, do stuff. And that generic T is not bound to a specific struct. We can pass in any type of struct we want into it, as long as it satisfies the other, I don't know, trait requirements or bounds. But the moral of the story is that T can be different types of structs. What happens under the hood for static dispatch is that at compile time, we know which structs that we're passing into this generic function. And what Rust does on its own in the compiler is that it writes a generic function that's specific to the struct that we're passing in, that we're using for that generic, and it writes all the individual functions for it. So let's say we have a generic function here, generic A, right? And we're passing in struct 1, 2, and 3, where struct 1, 2, and 3 are all different. The compiler knows this at compile time, so it's creating this version of this generic that is not generic for struct 1, 2, and 3 and writing it out. And then we're calling under the hood, Rust is using those mapping or those functions at runtime. So that's static dispatch. And the only reason why we can do that is because everything is known at compile time. What we're doing now in the trait objects is dynamic dispatch. Oh, so for dynamic dispatch, the compiler doesn't have the same information as it does for static dispatch. The compiler actually doesn't know what method you're calling, right? And because it doesn't know what method you're calling, it can't have this optimization that we're using in the static dispatch. Because writing everything out at compile time for the different struct 1, 2, and 3, that's an optimization. As such, since it doesn't have this optimization, it has a runtime penalty cost in terms of how fast it will go. But in this paragraph, they explain a few things that make a lot of sense in terms of the way it's written. So it says here, instead at runtime, Rust uses pointers inside the trait object to know which method to call, right? So the pointer is the box. And we're using a box, and then within box we have dyn, and then we have the trait name, which in this case is draw. So this is the reason why we have box, because it needs pointers to point to the trait object. And then the trait, the dyn, draw, dictates which method we're calling. And this is all happening at runtime. And because it's happening at runtime, there's a lookup cost, which I mentioned earlier. Other things to note is that since the compiler doesn't know about any of this, and this is all happening at runtime, the compiler cannot inline any of this code. So any optimizations that happen from automatic inlining, null and void, they're not happening here. And lastly, they say that doing this methodology, this dynamic dispatch, this trait object stuff, has gave us extra flexibility, and using it is a trade-off to consider in terms of how fast our code goes. Object safety is required for trait objects. You can only make object-safe traits into trait objects. Some complex rules govern all the properties that make a trait object safe, but in practice, only 2 rules are relevant. A trait is object safe if all of the methods defined in the trait have the following properties. The return type isn't self. There are no generic type parameters. I see. Okay. So here, they're saying there are rules to having something be a trait object. And there are many rules, but there are only 2 that are relevant. And that is that the return type can't be self, so you can't return self, which in terms of trait objects would break things because you're returning different structs. Like if you're returning self, you're returning a button and you're returning a select text box. Those are 2 very different things, and that breaks a lot of just Rust type constraints. And then the other thing is there are no generic type parameters. That would, having generic type parameters would add a lot of complexity. So I can see why they don't do it, but let's hear their reasons for it. The self keyword is an alias for the type we're implementing the traits or methods on. Trait objects must be object safe because once you've used a trait object, Rust no longer knows the concrete type that's implementing that trait. If a trait method returns the concrete self type, but a trait object forgets the exact type that self is, there is no way the method can use the original concrete type. The same is true of generic type parameters that are filled in with concrete type parameters when the trait is used. The concrete types become part of the type that implements the trait. When the type is forgotten through the use of a trait object, there is no way to know what types to fill in the generic type parameters with. Okay, so I'm starting to getting a sense of why that is. These things are important, these two things, and they're important for the same reason. Seemingly, when we do a trait object, at that point in time, Rust does not keep track of the concrete type. There is no need for it, and that might actually break things. But regardless, it does not keep track of the concrete type. So if you were to return self and then try to call a method on the concrete type, well, it doesn't know what the concrete type is, so that's breaking. And the same thing happens for generic type parameters. So for a generic type, there is a T, right? And that T is associated with the concrete type. But in trait objects, since they don't keep track of the concrete type, there's no way to know what that concrete type is for T, and thus that falls through as well. So these two things make a lot of sense in terms of why they have to be followed. An example of a trait whose methods are not object safe is the standard library's clone trait. The signature for the clone method in the clone trait looks like this. And so this is the clone trait, public trait clone, and it returns self. But because it returns self, it's not, what was the term called? It's not object safe. Thus it cannot be a trait object. The string type implements the clone trait, and when we call the clone method on an instance of string, we get back an instance of string. Similarly, if we call clone on an instance of vect, we get back an instance of vect. The signature of clone needs to know what type will stand for self, because that's the return type. The compiler will indicate when you're trying to do something that violates the rules of object safety in regard to trait objects. For example, let's say we try to implement the screen struct in listing 17s4 to hold types that implement the clone trait instead of the draw trait, like this. Okay. So here we're about to go over an example of how the compiler enforces object safety rules. And we're doing that by changing our screen. Instead of having a box to dynamic draw, which we already know is object safe, we're changing it to clone, which we know it's not object safe. And it's not object safe because it returns self, which is a reference to the concrete type. And this is the error that we would get. We would get this error: clone cannot be made into an object. And public components, clone cannot be made into an object. The trait cannot require the self sized. That is not the clearest in terms of error messages, but it does state that it cannot be made into an object. And this, we are talking about trait objects. So that is probably just the hint. This error message means that you can't use this trait as a trait object in this way. If you're interested in more details in object safety, see Rust RFC 255. Ooh. We have reached the end of this video, and I was not expecting this to be such a heavy topic. But trait objects look very, very useful. I'm glad we've gotten here. If you liked the video, hit like. subscribe. Outside of that, I'll see you next time. Peace.